So it is a pleasure and an honor to honor Yvonne, who has been important in my life as a scientist and as a man. So I will, indeed, I will try to give a brief introduction to some of the important contributions that Yvonne has given both to the mathematical aspect, but also the physical understanding, because for her, physics behind the theoretical physics description of the universe was very important and always in her mind. So I will not read this because the slides, but let me just mention here, in case I forget, is that she did not confine her interests just to the Einstein equations in a per se restricted, but she included extension of modern extensions of general relativity like supergravity and stringy type gravity. Okay. Now a few words. I will mainly talk about her accomplishments, but a few words about herself and her early career. First, she considered herself, as she wrote explicitly, as a failed physicist. She wanted to be a physicist, and her aim was always at understanding the real universe through equations given by theoretical physics by using and perfecting mathematical tools. Okay? About some biographical elements, as I will mention at the end, she wrote an autobiography, which exists both in French and in the English translation. So if you want to know more about her life, then please read her autobiography, A Lady Mathematician in a Strange Universe. And the father was Georges Bruhat. So I guess for most people outside of France, Georges Bruhat is not a well-known name. Actually, he was he did important contributions to optics, but he's mostly famous for writing many textbooks that when we were young we had to read. And even somebody like Grothendieck, when he said, I want to learn physics, then he was told you should read the books of Bruhat, which probably was better read Landau Lifshitz, but anyway. So anyway, these were high-level textbooks in physics. And something important in her life is both she recognizes here that her father had influenced her very much, but it must be said that he had more interest in his son, because, you know, like a blind spot in the autobiography of Yvonne is the fact that she has a brother, she had a brother, François Bruhat, who in the mathematics world is extremely famous for his work on Bruhat decomposition, although Sasha Goncharov was telling me this was known before, and his work with teeth on buildings and things like that. And anyway, in the family, both the father and the mother considered, okay, the brother is the one gifted, evidently, and you, Yvonne, maybe you can be a good mother and a good teacher in the gymnasium, you know, and things like that, but okay. Anyway, Yvonne resisted the pressure from the family and she said, I want to do research. But there were more obstacles in the sense that she followed lectures by Jean Leray, and then Jean Leray suggested something, and she wanted to choose as topics what was the main result of her thesis, which was to prove existence of solutions, well-posedness and non-analytic solution of Einstein's equations. And then she went to her official thesis advisor, André Lichnowitz, and André Lichnowitz said, this is too difficult for a debuting scientist. But she was not, then she went back to Leray, and Leray said, okay, if you want to do it, you will do it. And she did it. And indeed, by the way, there is a very nice recent article by Yvonne in 2014, Beginnings of the Cauchy Problem, where she says explicitly what happened. Okay, so she followed the lectures of Leray. Then Leray said, you should read Schauder. But then what happened is that she looked for a paper of Schauder which was relevant, but she did not find a good paper. And then, but she found a paper of Sobolev, which was improving on the Hadamard construction of the parameter of the Green's function. And then she said, now I have a tool, and therefore I will use Sobolev, which is what she did. Sobolev was for the linear case, so she had really to do the hard work of proving for Einstein nonlinear. And then she proved the theorem that Sergio will comment more, but I will make a little bit some comments about it, in a space of smooth functions, okay? And so what is, first this theorem was announced in a note to the compte rendu of the Academy of Sciences in 1950 when she was 26 years old. This is this note. I'm saying that because this note has been recently republished, I mean in English translation, as a golden oldie in 2022 with a very pithy editorial note by Demetrios Christodoulou. I will mention something. Anyway, then it was published in the full detailed version in 1952. By the way, it was presented by Hadamard to the Academy of Sciences. So she proves actually a more general theorem than is needed for Einstein's equations. Well-posedness of the Cauchy problem for quasi-linear diagonal systems in 4 dimensions, although one has to check whether all elements of the proof is really quasi-linear or hyper-quasi-linear.
I don't think she includes a derivative.
Yes, I know. That's why I'm saying this, okay? I'm aware of this. No, but in the thing, this is included, okay? At the beginning, she says this. And part of it, it's true, okay? But at some stage, she needs hyper-quasi-linear, okay? Now, let me just comment something. I don't know if you will comment in the, you know the editorial note of Demetrios, no? Yes. Or not? Okay. In this note, Demetrios insists on the fact that working with the initial condition which for the Cauchy problem with smooth function, you have the problem that you lose one derivative, okay? And he wonders why she was not using energy estimates, but the point is that energy estimates, she did not find the paper of Schauder, and then Leray was developing actually energy estimates while she was working on this, but Leray told her, continue with your method because it is constructive and it's good to have also smooth functions. And the last point is that Christodoulou points out, and you will, I guess, comment on this, that the fact that you lose one derivative is linked to the breakdown criterion of Kleinerman and Rodniansky in 2008, okay? So, and anyway, the constructive character is important. So the content of this initial work by Yvonne is to solve the Cauchy problem for Einstein's vacuum equations using the structure. And the point is that here in this paper, written in 51, published in 52, she understood very clearly that for non-analytic data, you can see gravitational waves and gravitational rays and propagation phenomena. That is to say, you see the domain of dependence, that if you have data, the solution here depends only on the data here at time t equals 0. And the point I want to make here is that this very clear understanding that this was proving the existence of propagation of waves in 51 was at the time where many physicists were confused. In 51, there were even many physicists saying, like Leopold Infeld, that gravitational waves did not exist, that this was, you know, gauge effects. I mean, people were confused, and physicists only in 1957 with Joe Weber, Trautmann, Pirani, Bondi, Feynman, and the work of Louis Bell in 58, that physicists understood that indeed gravitational waves is a reality in physics. Now, this initial work, she generalized to Einstein-Maxwell immediately in 4 dimensions. She generalized it to solutions of Einstein equation in any dimension in 53 under the name of Choquet-Bruhat, all these early papers. Then she added perfect fluid, okay? And she insists on the fact that these evolution equations starting from data, in some cases, like the the equations of physics, which are at a more fundamental level, they are hyperbolic, Leray hyperbolic. But when you come to more phenomenological, like fluids with dissipative finite conductivity, then they become non-strictly hyperbolic, which is Leray-Oya, which means you don't have solutions in good function. I mean, you have solution in Gevrey spaces, okay? But anyway, and then she generalized an important result with Guéroche in '69 is geometric global uniqueness. Then she discussed supergravity, both in simple supergravity and the n=1 supergravity of Bernard Julia, Scherk, and where is Bernard ici? Scherk and Eugène Kremer, okay? And recently she worked on the light cone formulation. So now another, apart from the Cauchy problem for many equations of physics, she did important contribution on the 3+1 decomposition of space-time. In particular, now when you want to solve Einstein's equation on the computer, you need, you don't solve immediately the full, you don't look for a full space-time, you give data at t=0, which is supposed to be some slicing. I mean, you have an initial hypersurface in space-time, you give data there, and then you evolve them in time. And the question is what equations you use. And let me just mention, and in the following slides, there are several conflicting notations just to decompose in 3+1 the metric. So you have a metric in space-time, and sometimes you decompose the spatial metric on the slice is sometimes called Hij, sometimes gamma ij. Then you have gauge degrees of freedom, which is the slicing between one slice to the next, and then the choice of coordinates in each slide, okay? Alpha and beta. Now, I say this because in the literature, most people say it's called the ADM decomposition for Arnovid, Deser, Missner, but actually this was first fully written down by Yvonne in 1948 and in 56, where she wrote explicitly Einstein's equations decomposed with lapse, shift, and the metric. And also in this paper, she was the one to first discuss methods for constructing general solution of the constraints. What are these constraints? So when you state the Cauchy problem for Einstein's equation, which means you say, I want to start from a state of the gravitational universe at time t=0. In geometrical terms, it means I select one slice, space-like slice of space-time. On this slice, I have two types of geometrical data. In physics, in mathematics, they are called the first and second fundamental form, which means the metric on this thing, and then how the metric varies when you go orthogonally away from this metric, the second fundamental form. And Einstein's equations tell you that these data of the first and second fundamental form are constrained by four equations. One scalar equation which contains the square, which is a Gauss-Bonnet equation, which contains the square of the second fundamental form and the Ricci scalar of the first fundamental form, and a second equation which looks linear, except that there is a metric here, which says that the divergence of the second fundamental form is 0, essentially. Except that when you have sources like energy density or momentum density, then you have sources on the right-hand side. For vacuum, this is 0, this is 0. So Damour, in 1927, Georges Damour, who was actually the creator of mathematical relativity in France. I mean, Lichnovitz was a student of Damour, Racine was a student of Damour, okay? In 1927, explicitly wrote in his beautiful small book, these equations. Here you can recognize the second fundamental form, and then there are the constraints equations. Okay, but there is a very nice, so the article I was mentioning before of 2014, Beginnings of the Cauchy problem, contains a nice account by Yvonne of the problem now of solving a constraint, because to solve the evolution of Einstein's equation, you first need data, first and second fundamental form, that satisfy the constraints, and then these constraints are propagated, okay? So, but you need to satisfy them on the initial slice. Now, the first person to do an important contribution was Racine, who is often forgotten because this equation is usually called the Lichnerowitz equation, but it was written by Racine in 1934. That's why the paper of Yvonne is very clear on the early history. And so what Racine did was, let's decompose the metric in the initial slice in a conformal factor to the power of 4 and a background metric that you choose. Here denoted gamma in conflict of the previous slide. But anyway, I did not want to retype all equations, so you know it's convenient to take equations here and there. Anyway, these equations look like this, and Racine noticed that if you choose, which looks really a very coarse approximation, the initial metric is conformal to the flat metric, Kronecker delta, then you get a system, half of it is linear. There is a system which is linear for the second fundamental form. And then you have an equation for phi, which is non-linear. But if you take, as we will do later, the even simpler case where k tilde ij is 0, which is the solution, then any solution of Laplace equation gives you a solution of the data, okay? And this will be very important. Okay, now, for many years, as Yvonne insists, these people did not look really as the structure of this system of constraints, what is the space of solutions, and she started doing that in 1961, showing in particular that if you use harmonic coordinates, actually you have an elliptic system for the Gothic variable 0, 0, and 0i. And then a student of her proved that this leads to solutions. And then there was the work with York. YCB means Yvonne Choquet-Bruhat. Okay, and solutions in Hölder spaces. Okay, let me not enter into the details. The second topic I want to talk about, although this will be covered in more detail by Cécile Huneau, is about strong high-frequency gravitational waves, because physicists, starting with Brill-Hartel in '64 and then Isaacson, had understood that if you take weak gravitational waves, a small perturbation of Einstein's equation, so you start from some metric, then you put in the usual WKB approximation, you put a wave which is made of sine and cosines with a high frequency and a small amplitude. But if the amplitude is not so small, actually, you find that the nonlinearity of Einstein's equations means that the square of the perturbation will contribute and modify the background. Now, when physicists were doing that, they were using not well-defined averaging techniques, and it was not so clear what one was constructing. So she put clarity in there by using the two-timing method coming from Leray and Gording, Kotake, and Leray. So she gave a very clean discussion, and then imposing. So now what she proves is that if you look for solution of this type, with omega going to infinity, and if you ask what is formal series solutions of this type, then you get a system of equations saying that you see the econal, you see that the phase satisfies the equation of null rays for gravitational for the lines generating phi equal constant. And then what she insists upon is that in general, you get a propagation equation which contains nonlinear terms, but she insists and she proves that Einstein's equations have a special structure. And then it was understood later by Demetrius and Sergiu that this is linked to the null condition. I mean, there is this special structure in Einstein's equation that they are quasi-null or whatever, I mean, depending on the gauge, okay? Here, the fact that they are quasi-null means there is a back reaction. If they were really null, there would be no back reaction. Anyway, then at the end, she proves that these high-frequency waves deform the background by something equivalent to having a null fluid, I mean, gravitons propagating at the velocity of light. Then she worked, apart from this initial work, she did many other works, like generalizing this to the case where there is Einstein-Maxwell. And in the Einstein-Maxwell case, She was one of the first to understand that there is interconversion, in the sense that if you have an electromagnetic wave propagating in an electromagnetic background, then it's slowly converted into gravitational waves. You have oscillations, like oscillations of neutrinos, waves that, okay, due to nonlinear interaction between Maxwell and Einstein, okay? So this is an important thing. Then couple fluid waves, Young-Mills, spinor fields in stringy gravity. And let me mention that this afternoon, Cécile Huneau will pose answer the following question. What Yvonne showed is the existence of formal solutions in a formal power series in omega to some order. And then recently, through the work of Cécile Huneau and Jonathan Luke, and of Arthur Tuati, who is somewhere here, one has constructed sequences of exact solution of Einstein's equation and showed that in the limit, it is not a solution of Einstein's equations anymore because of the back reaction. Anyway, another important topic where Yvonne introduced got important result was in 1976, following on the footsteps of physicist proof by Dieter Brill and Stanley Deser. She gave the first rigorous proof of the positive mass theorem, positivity of mass for a vacuum spacetime, which means the total mass seen at infinity, total mass in the sense of Felix Klein, because he was the first one to write this formula, and Arnold Deser-Misner, is positive by using critical point analysis in Banach spaces, in infinite dimensions, having the good conditions to prove something, really. This is this paper with Marsden. Let me also mention that one of the last research papers that she did while she was here was an extension of the spinorial proof a la Ed Wheaton in all dimensions in 2011, which is a very clear and sharp proof. But you have to assume the spinors exist on the space-time you consider, on the space at least. Okay, now concerning this 3+1 formulation. So for numerical relativity purposes, representing Einstein's equation in the evolution of a metric as a function of time, slicing, is important. And if you use the equations written down by Yvonne or Arnold Deser-Misner, then you get this system of evolution. And for many years, physicists naively said, oh, this is the first evolution system for the first and second fundamental form. In the right-hand side, I have functions of the first and second fundamental form and gauge parameters, gauge functions, n and ni, so I can choose the lapse and the shift to some given function of space and time, and then I can solve this evolution system. It should determine the thing. And for many, but then when you do that, it leads to numerical instabilities. If you do this, immediately you cannot, the code crashes, okay? But still, actually, there is a nice result of Yvonne, which is a recent one, in the sense that it is only in her book in 2009, that she proved that this system with fixed lapse and shift, given, is hyperbolic, not strictly hyperbolic, so it is a Leray-Oya system. So in principle, if numerically you could have Gevrey data, then they would propagate as Gevrey class data. But evidently, numerical data are never Gevrey, because they are not smooth enough. That's why there are instabilities. Anyway, another important point is, as I will say, numerical relativity has, after 30 years of work, has succeeded in solving Einstein's equations on the computer. And the way it was solved, what I will explain now, is the method that succeeded in doing this. They used results that were coming from previous results of Yvonne. They did not use results, immediately Yvonne result changes the game, but Yvonne results change something, which changed something, and then it changed the game at the end, okay? So this game changer results by Yvonne was first a work of 2000, when is this? Anyway, of 1982, sorry, early work, with Tommaso Ruggeri, where they showed that if you take this gauge condition, which fixes the slicing n in terms of the determinant of the first fundamental form, which is equivalent to saying that the time coordinate alone, t or x0, is harmonic, but not the space coordinates. You just take harmonicity of the time coordinate, then, and you fix the shift to either 0 or later generalize with York to something, then you have a Leray hyperbolic system, okay? So it shows that there are gauge conditions that are very good for the numerical evolution of Einstein's equation. And then she wrote explicitly this system, which is second order in this variable k and first order in g. And what the point I'm making is that not directly this system, but some things inspired by this system has been important, because the condition imposed by Yvonne and Tommaso was of this type. This is the harmonicity of time for the lapse. Now, Bona and Masso said, but if I put a function of alpha on the right-hand side, instead of alpha square, I put something which transforms alpha square in 2 over alpha, then, maybe there is a misprint here, but anyway, something, at the end it's 2 over alpha. Or maybe not, but anyway, it's -2. Then you get the so-called 1 plus log thing, which is still used. I mean, for instance, yesterday we were discussing with one of the experts, I will mention his work later, on numerical relativity to do high energy scattering simulations. They use this, okay, today. And then you need a condition to fix the coordinate, spatial coordinates in each slice, okay, which is called the shift. And then you use conditions which are called minimal distortion, like Alasmar-York and gamma driver, okay? And then this formulation, now they became named as BSSN. And also an important thing where Yvonne did not contribute immediately, but which is the fact that the recent codes, there are 2 types of codes. One which uses harmonic coordinates and where you see that there are black holes in space-time, and another type of code where you replace black holes by punctures, which is just a singular point in each slice, okay? Now I want to, it's a beautiful story, and I want to say to mathematicians here, especially young mathematicians, that maybe there are things to do mathematically to clarify what's going on here. Because so this is one way to have the evolution of 2 black holes. Black holes are complicated objects, okay? In space-time, there are horizons and all that. But what you do is the following. You start with Racine 1934, that nobody ever cites. And Racine 1934 would say that if I take the simplest case that the metric is conformally flat initially with a phi to the 4, and then you get this linear system, okay? And in particular, if you take the time symmetric situation where the initial second fundamental form is 0, you have just to find solution of Laplace equation, and that will give you solution of Einstein's constraints. And the simplest solution of Laplace equation for physicists is 1 over r, okay? The fundamental parametrics. And then if you take 1 over r, what solution do you get? Actually, you get Schwarzschild solution, because let me remind you that if you take Schwarzschild solution, the black hole, in isotropic coordinates, which means you don't use Schwarzschild coordinates, but these coordinates, the spatial metric is the 4th power of 1 plus m over 2r times dx squared, the flat metric. So indeed, this simple Racine type thing. But then, what happened? In 1935, because it's nice to see the story of this, Einstein and Rosen understood that if you take this thing is invariant under an inversion where you change r in 1 over r with a fixed radius being m over 2, this m over 2 which is here. So you do an inversion between large r and small r. And when you do this inversion, you find that the geometry of space is this, okay? Is made of 2 sheets, which is called now a wormhole, or actually it's an Einstein-Rosen bridge. But the point of Einstein-Rosen actually was to say, when you have the problem of motion of 2 bodies, you should look for a solution of Einstein's equations, which is made of two bridges going to the same two spaces. One space, another space, and two wormholes, as people would say today. Missner has constructed initial data that satisfy this Einstein-Rosen thing, but then Brill, the same Dieter Brill, and Lindquist in 1963, they said, but there is a simpler solution. That is to say, we are solving Einstein's equations, Laplace equations. So instead of 1 over r, why don't you put 1 over r1 and 1 over r2? You take two masses in flat Newtonian space, and the 1 over r potential generated by the two masses is this. This gives an initial data solution for Einstein's equation, which is used today. Like yesterday, we were discussing, the scattering of high-energy black holes. The initial conditions are Brill-Lindquist, okay? Where you add the Bowen-York thing, but essentially, so it looks extremely naive. You say, what is Newtonian thing has nothing to do with Einstein, but it gives initial data for two black holes. But then what happened is, thanks to the NID, then where did I cite Brugman? Yes, it was cited before, yes. So Brugman understood that if you start with this data, Brandt and Brugman said, if you start with data like that, you generalize them like Jimmy York had indicated by adding momentum or spin on the two objects, so it's like another solution. Then you need to solve now the Racine-Lichnerowitz equation, which is of this type, which is nonlinear. And the beautiful thing is that although you give data where in space R3 you have two singular points, this equation has solutions for you, which is C2, which is smooth. Okay, smooth in the sense two derivatives exist there, okay? Because this is singular, but they compensate and they give zero. It's overcompensate. So, and the idea of then Brugman and his group, which is used every day in numerical simulation, is to say, these are initial data, but let's evolve them. And then the point is, what happens to the two singular points? These two singular points, in a sense, they mark the location of what would be black holes in space-time, but it is very convenient because you can make them move if you use good gauge condition. And this is the way you solve now Einstein's equations half of the time. And then, just to say that, at the end, the two punctures, they become trumpets. They don't really give like Einstein-Rosen. They have infinite trumpets. It's not very clear what is the geometry of this thing, but it works. Now, another big recent works on numerical relativity which descends, in a sense, more directly from Yvonne, is using harmonic coordinates. And except that, Yvonne had proven long ago that if you use really harmonic coordinates, then you transform Einstein's equations, which are neither hyperbolic nor elliptic nor nothing, into a quasi-diagonal hyperbolic system. Loret type, hyperbolic in the Damour sense in that case. And this was, and then the constraints propagate. So the constraints means the condition you impose that the harmonics are that the coordinates are harmonic. So if I define C like the D'Alembert operator acting on the coordinates this way, Einstein's equations, when you, so here reduced by this condition, you find that the constraints that you must satisfy, the fact that the coordinates are harmonic, is propagated because it satisfies this thing. So this is part of the thesis of Yvonne. But now, numerical relativists have found that you need to modify this system in two ways in order to be able to describe the motion of two black holes and the coalescence of two black holes. The first way, which was suggested by Garfinkel and Friedrich, Helmut Friedrich, is to say, instead of imposing that the harmonics, that the coordinates are harmonic, you say that they satisfy something with the given right-hand side, generalized harmonics. It's not a crucial step, but you say that this is equal to some function you give, or function that you give an equation of evolution for. But the most important thing is, and this was understood by Gundlach and others, but Praetorius was the first one to understand that this was a crucial new thing, is the constraint damping terms. That is to say, if you write Einstein's equations under this condition, you get this system, okay, equals 0. So you get a quasi-linear system of evolution. This system is okay. Mathematically, it would propagate everything. But the problem is that when the constraints are 0 initially, they should remain 0, but you have always numerical errors. So therefore, they don't stay exactly 0. So, but what you can do is you can add these terms with a positive coefficient kappa. You add the constraints such that at the end, the constraints satisfy this system with an extra term, which is a damping term, which means the solutions will decay exponentially. And because of this, even if you make small numerical errors, and even if you accumulate small numerical errors, the constraints will go towards 0. Okay. This was apparently the crucial step, which was a rewriting of the original system of Yvonne, you know, in the form. And then what happened is that in 2005, Franz Praetorius, who was a young postdoc in Caltech. By the way, there was a big group of people doing numerical relativity next door. We were trying to do things, but he did it alone. And then he discussed with Gunla. He read the paper of Yvonne, probably, and then he understood what to do. And then he was the first one to be able to evolve. Actually, this were Einstein's scalar field, because you create the black holes by the collapse of a scalar geon, okay, like Johnny would say. And then he was the first one to obtain the curvature tensor at infinity, so-called psi4 of Newman-Penrose. So one radiative component of the curvature, or it's called alpha bar, yes, sorry, in the works of Demetrius, Sergio, and Jeremy. Anyway, it was the first one. And then you see that the numerical errors are not small, because depending on the accuracy of the scaling, then you get different answers. Then a few months later, Manuela Campanelli, Carlos Lusto, and collaborators, they use the moving punctures. So they say black holes is complicated. Let's use the 3+1 decomposed BSSN with this gauge condition and punctures a la Brugmann, but moving punctures. And then they could get things which are used every day today also to compute what happens when you have two black holes, either merging or scattering. Anyway, I want to finish by mentioning two open problems in mathematical relativity for the future that I hope the mathematicians interested in physics and in relativity will tackle, which need clarification. So one is explained in a chapter in the book of Yvonne of 2009. This is the generalized Belinsky-Halatnikov-Lifshitz conjecture. So if you look at the section 9 in the book of Yvonne, so what is this about? If you open the famous treatise of theoretical physics by Landau-Lifshitz and the beautiful chapter on general relativity, actually it's a book on field theory, and 2/3 of the book is about special relativity and Maxwell equation, and then general relativity is condensed. The essence of general relativity is explained, including cosmology, in the last part. And this book is still, that's where I learned general relativity. I mean, I learned general relativity from Schnorwitz's book and from this book. Then what you find is it's a conjecture which says if you look at so this is a general solution of Einstein's equation in some gauge with zero shift, but a special way of choosing the lapse related, which is linked to the condition of Yvonne with the square root of g. And then you choose a frame which is the same in all the slices, time-independent frame. And then the metric, the time dependence of the metric is contained there. Then you decompose this metric in an Iwasawa decomposition, which means you define diagonal components and upper triangular parts in an Iwasawa decomposition, but then it defines a metric with components up and down, which means you have decomposed the metric in the logarithm of the diagonal components that you call betas, and into the other variables, the off-diagonal variables. Now, so the idea is, and this is what is in the Landau-Leaf sheets, in 3+1 dimension, it was argued that what happens when you go towards a space, the generic solution of Einstein's equation near a big bang or a big crunch, that is to say, you have a space-time which evolves, or which evolves from something or towards something. Nobody cares about the sign of time. And the slice t equals 0 is singular. And there, in this chapter, one has formulated in the best possible way a mathematically precise conjecture. So the mathematically precise conjecture is when you go there, that the generic solution, or let's say an open space of solutions, is when you go towards the crunch, is that all the off-diagonal variables, they have limits, okay, limiting functions, and all the dynamics is contained only in the diagonal parts of the metric. And when you take the logarithm of the metric, which means, in a sense, the metric becomes, first the space crunches. So the volume of things, I mean, you go to a singularity where everything crunches, but it does not crunch in an isotropic way, like it crunches where some directions still expand and others crunches more and things like that, depending on the dimension. Then it was shown that the variables beta, they satisfy in the limit ODE, Hamiltonian system, which is a billiard in some Lorentzian space. And what is interesting as a side remark is that this billiard is the billiard in the Weil chamber of an hyperbolic Kac-Moody algebra, which would be E10 for the supergravity of Bernard, Eugène, and Joël. As we have shown, we have a paper with Bernard Julia where we looked at Einstein's equation in all dimensions. And then what happens is that in dimensions, space dimension 3, 4, up to 10, you have 10 excluded. You have an hyperbolic Kac-Moody algebra which is there, but it ceases to be hyperbolic in 10+1 dimension, and then it is replaced by E10 anyway. So this is a conjecture which is open, and I've been pushing Sergio for years, saying maybe you should work on this. Now another...
That's a life.
You have only one life. Yeah, you have achieved a few things in this life already, but you have plenty of time. Now, there is something striking when you think about cosmology, is that our real universe looks like this, okay? This is a recent photograph from the James Webb Telescope, okay? It's extremely inhomogeneous in the sense that there are stars, there are galaxies, matter is not now uniformly scattered. And for many, many, many years, physicists were aware of this. Einstein started saying in 1917, let me approximate all the stars as being scattered in dust all over the universe. What is a simple solution, okay? Then Friedman came along and said, it needs to evolve in time. And then you find that if you take isotropic and homogeneous universe, you get the so-called Friedman solutions, or Friedman-Lemaitre, or Friedman-Lemaitre-Robertson-Walker solutions, which are very simple. And they are even simpler in the sense the modern data said that you are spatially flat to a good approximation. So it is an expanding flat space, and you add minus dt squared. And then you add perturbations to it. The question is, are you sure that these perturbations are small? In what sense they are small? In what sense the Friedman-Lemaitre universe is a good approximation to our lumpy universe? This question has been discussed by physicists over many years. Actually, the first good answer was given again by our master, Einstein. Einstein and Strauss, in 1945, they proved that they constructed the so-called Swiss cheese universe. They did not call it Swiss cheese, it was called Swiss cheese later. A Swiss cheese universe is a very beautiful, exact solution of Einstein's equation, where you start from a homogeneous isotropic Friedman universe with constant density all over space, and then you take a ball somewhere, and then you say, I will empty the ball from all the matter it has, except that I put all the mass at the center. This is, I put a Schwarzschild solution at the center with mass equal to what would be contained in this volume. But then the beautiful thing is that you can start again. This is where the Swiss cheese comes in, although it should not be translated in French by Gruyère, because as you know, Gruyère has no holes. But anyway, there are Swiss cheeses with plenty of holes, in the sense that if you take away one chunk spherical symmetric, another one, so you have a universe which is made of many holes with masses in the center. The evolution of this is still, the global evolution outside of the holes is described by the Friedman universe. And everything is C1 at these things, okay? But this is under the condition that still you put exactly this mass there, okay? Why it's not exactly the situation in our universe. Now, in usual physical theories, like in when you solve Maxwell equations in a medium, you don't say that I have an atom here, an atom there. You say I have an average density rho, an average current, and because it is a linear equation, the solution is well approximated if I change the source. And always in physics, people say, yeah, but Einstein's equations are non-linear, so there should be strongly nonlinear effects at some stage and things like that. And the debate continues over the years. Let me mention, in particular, Thomas Buchert has been claiming that indeed, like for the high frequency waves of Yvonne, the square of the small perturbation, even if they are small because they are lumpy, will create a big back reaction, which maybe explains dark energy and everything you don't know. But there has been a recent set of works by Green and Wald, where they introduce what they call a new framework, which is, and the question is, that I'm asking mathematicians, and Arthur knows very well these papers, so they say, let's frame this in terms of a sequence, okay? And the question is, I have this sequence where the lambda, when lambda goes to 0, I have high frequency features, okay, but still h goes to 0, so that the h1 goes to, in the L infinity norm, the perturbation of the metric would go to 0, but the derivative would not go to 0. And then what do you get at the limit, okay? And they say they have theorems. I would like to know if these theorems are really theorems. And anyway, I think it is an interesting open problem to clarify this situation. Now, to end, let me say that besides our many research papers that had a lot of influence in the field for years, Yvonne had also a very deep impact for generations of young mathematicians and young theoretical physicists through the many books that she wrote. I admire her because I never wrote a book, you know. And did I? I mean,
popular.
Ah, yes, popular books. Yeah, even a graphic novel. Yes, if you want to understand quantum mechanics, there is a graphic novel about it. But here I'm talking about books, scientific books, with equations. So that started in 1963. Then there is this beautiful book on exterior differential systems. Then the famous books with Cécile, which have been used by generations of young people. Then in 2009, the big book on Oxford University Press on Einstein's equations, which still, I think, contains hidden treasures to be looked at. She wanted to, to leave this, including reprints of her papers. One has to read this book, okay? And she was 86. And she was 86. And then she was asked by Oxford University Press to write a textbook for students. And then she wrote this beautiful introduction to general relativity, black holes, and cosmology, where I learned things. And then the last effort of her was to write an autobiography.
Thanks to you, because you suggested it.
Yes, I pushed her, I discussed, yes. All this we discussed a lot. And so I wanted to end just to say happy 100th birthday, Yvonne, and thank you for everything you have given us. And yesterday I looked for pictures of Yvonne here at IHES, including with my dog, Ulysse. Okay, thank you for your attention.
Thanks, Thibault, for the beautiful talk. So, are there some questions?
I just had a comment, not on the science. I forgot to say how much she was thankful to you to welcome her here when she retired, and she was really very happy to come here every week, even if she broke her arm on the way from the station once. And she loved the exchange with Thibault, but also with the other people, and it was a pleasure also for her to see again Cécile while she was here, because she was her big friend. And so it was really nice.
Yeah, this is Cécile de Witt here. I mentioned my dog, but not Cécile.
Yeah, for the end of her career, it was really an highlight to have the possibility to come here and to have exchanges and to continue to work.
Thank you.
Nathalie had a question.
You mentioned that you didn't talk about her contribution to Einstein Gauss-Bonnet. Could you
Yes.
give a short summary? Because it's I remember I discussed it.
Yes. So, although there is a paper by Yvonne called Cauchy problem, okay, on Einstein Gauss-Bonnet, she, actually these are incomplete results, but if you read the paper, you know, she says even the characteristics are complicated. So not to mention, so you are beyond any proof of evolution of data. And I think maybe she does not discuss the constraints or whatever. But anyway, she was aware that, but there is a discussion. She relates that to the work of Vaillant. So I don't know if it has been in your work fully clarified. What is the full structure? She says it depends on how the characteristic cones. In some cases, she says, yes, if the Gauss-Bonnet parameter is small enough, the cones will be well thing. So I think she did not contribute more than this, yes.
Yes, but she showed that there would be problems anyway in the evolution.
Yes, yes. She also showed that the characteristic change sign at some point. I mean, if the curvature is too large, the characteristics are no longer hyperbolic, but they are elliptic parts. Yes, yes. That shows her interest in many things linked to physics.
Other questions? Okay, maybe I have one question on the last conjecture you mentioned about the high frequency limit. So, as you mentioned, Cécile, we'll talk about it this afternoon. But this is so. Is it a different type of weak solution?
These ones of Greenwald.
Yeah.
Yes, because here, okay, they say, but Burnett was a student of Wald, so they say. They never cite Yvonne or whatever. They say Burnett said it's good to have sequences. And then that's why I wanted the eyes of mathematicians, because then they say theorem 1, theorem 2, and which seem to be very clearly stated, you know, if this is in some functional space and this is locally in some L infinity, then you can control, and they say that under conditions that has to be specified, because you need to say which functional space this is in, that the correction to the T mu nu, you start from a solution of Einstein's equation with a real T mu nu, and then you ask, like for the high frequency solution, does the limiting thing, because this limiting thing is supposed to be the Friedmann-Walker universe, the Lemaitre-Friedmann universe, and you want to know whether this thing satisfies an Einstein equation with an average T mu nu, or whether there is a contribution from the square of the fluctuations, like in the high frequency. And they say this contribution, one of the theorem, I think, is that this contribution is as a positive sign. I mean, it satisfies the weak positivity condition, and therefore it cannot explain dark energy, which has, okay. So that's what they want to conclude, saying against what Thomas Buchert is saying, this cannot explain this. But, okay, I know that when I discuss with other people like Alexei Starobinsky, he said, it's enough, I have proven there exists a gauge where everything is small, so we don't care, we know what is the Friedmann thing, and that's okay. Because physicists usually have in mind the Swiss cheese universe, which is a very striking thing, okay? At the same time, I should say that very early on, this picture is taken from a paper of Kantowski. And actually, Kantowski said, yes, definitely, in the Swiss cheese universe, the evolution of the universe is given by Friedman. But if I now do some measurements of seeing lensing and the lensing, the cone, when you look at objects far away, you get light, but this light will go through the holes, okay? And therefore, they will go in a part of the metric which is not the Friedman, okay? It's not like going in a homogeneous. And then he started saying, but the difference will be small. And then later people like, several people said, but in some cases the difference can be measurable, so they are not so small. So, and then there is the debate, it depends on the observable you look at. You want that the background solution G0 can be well described by a Friedman universe with some mu that you know, and the question is, okay. Anyway, you have to read this. The question is, I did not have the time to read in detail these papers. The question is, it's an interesting, I think, a mathematical problem. I think Arthur is thinking about it. It's Cécile too. Ah, sorry.
Okay, so thank you very much. Thank you again, Thibault, for the beautiful talk.